Hi, welcome to my extended presentation on mapping simulated clusters using Illustrious Python. My name is Darion Blakesley. I recently graduated out of Arizona State this summer in mechanical engineering. Uh, my mentor is Bhuvnesh Jain, who's working out of UPenn, along with a colleague I didn't list here, but his name is Sam Goldstein, and he helped me immensely throughout the project uh, in processing some of this data and getting used to Illustrious Python. Yeah, so I don't really mention it in the rest of the slides, so I'll kind of just touch on it here. Illustrious Python is a Python library uh, that allows you to work directly with these large-scale simulations from Illustrious. Uh, and it's all online, so um, uh, yeah, free for anyone that's interested in this sort of thing. Get right into it. So, exploring the intracluster media. This is a hot ionized gas that permeates the galaxy clusters, and because it takes up such a large volume of space, it actually accounts for a relatively large fraction of the total cluster mass, uh, much greater than that of the galaxies themselves, but not quite as much as the dark matter. Uh, Nevertheless, it's really important when you're um, trying to characterize the clusters themselves and or analyze them. So here I included an image of a cluster gas distribution for the simulation that I'll be using towards the end of the presentation. This is a TNG illustrious TNG 100-3 simulation. And these numbers are just have to do with the resolution of the simulation, the size. Right, cluster gas distribution. Um, so I was given data from a set of 9 halos, so 9 very massive halos actually. Uh, and so what I wanted to do just to get some intuition on uh, on the density and the clusters overall, I plotted them, and so you have y y position and x position on the axes, and then they're weighted by just the count or the density of gas particles. So, one other thing, which you'll see here is a little plus sign. Hopefully, you can see it, and that's denoting the center of mass of the cluster, uh, which you'll notice is a bit offset from the gas center of mass, or the gas's center. This is because there's also dark matter present in these clusters, and it's actually pulling away the center of mass from the gas center, right? Uh, so you might think that the dark matter and the cluster or the cluster gas are both very massive uh, objects, and they kind of pull towards each other and overlap. But this isn't necessarily true, um, just because of the age and activity of the clusters themselves. So other than that, you'll want to look at the shape, size, symmetry, and density of the clusters, and these are also factors that will help you to characterize the clusters and their age and their activity. So throughout the presentation, I'll be kind of staying on Halo 1 and Halo 3. And now I had a set of 9 halos, but I thought these were just the um, two most interesting to kind of compare and contrast as far as how their qualities are working out. Uh, so you'll see that they have some differences as far as their density and size. Uh, Halo 1 looks like it's pretty sprawling, and Halo 3 is kind of just very compact and orderly. Uh, but then they have similarities in their actual shape. Temperature distribution. So these are very similar to the plots before, and they show the X and Y position on the axes but now they're weighted by temperature. And yeah, so if you look here, you can kind of see this color map will tell you the temperature of the actual gas particles. One thing about Illustris, it does not directly give you the gas temperature, but rather you can calculate it from the electron abundance of the gas and the internal energy of the gas, which is all pretty well documented. Um, yeah. So some observations that can be made here is that Halo 3 is much hotter, and it's a lot more dense. And it also has this virialized, which is cosmologist jargon for relaxed or settled temperature distribution, where Halo 1 has a very asymmetrical or disturbed distribution, um, which can be the result of mergers. This had recently accreted um, some matter that could heat up this region. Um, yeah. So to get a little bit more insight on how temperature and density are related, I plotted them together. And as you can see, the Halo 1 has a very inconsistent relationship with temperature and density. It looks just kind of like a scatter plot, like a blob. Um, Whereas Halo 3 has a fairly linear relationship, actually. It's worth noting that this is on a log axis. So this isn't truly linear in nature, but it does speak to the fact that there is definitely a relationship here, uh, whereas there's not much to take away from this. And this is kind of intuitive when you look back at these plots. This seems like to be a fairly uh, uh, a fair relationship of temperature as you move towards the outside of the cluster. All right, uh, so that gives some information on the relationship within one halo itself. But uh, a better question would be, is what is this trend across all halos or many halos? So for that, I familiarized myself more with Illustrious Python, and actually was able to access uh, the entire simulation itself. And so what I did was I made two mass bins. So I made a low mass bin and a high mass bin uh, to see if they would behave differently. And I grabbed 700 random halos from the low mass bin, and then 700 random halos from the high mass bin, and kind of compiled them into an aggregate data set to look at the underlying trend. And what you'll see is the simulation data points to a departure from the expected relationship at these higher mass clusters. Right. So I didn't talk about it yet, but the expected relationship for a temperature density relationship for something like this uh, would be actually just like this. So a negative slope. This is because the cluster gas is described uh, as a perfect or an ideal gas. So, which would work out that the density and temperature are are uh, inversely related, or right. So, which on a log scale would look something like a negative slope. But these high mass clusters don't really show that, right? So it's not working out that same way. So what would be interesting to see how real data uh, from cluster gas plays out, and if it would also show this departure from the expected relationship. Yeah, so that's what I worked on this summer. Um, like I said, I have a background in mechanical engineering, so this is a lot of this was very new to me. But I've always had a passion for physics, and was the reason I went into engineering. So kind of getting some headway into this and kind of understanding what questions to ask in this field was very valuable for me. Um, and really, I'd hope that students from all backgrounds, uh, from all STEM backgrounds, could get a hands-on taste of cosmology like I did, and uh, really develop that interest in it. So, thank you for watching. I hope you enjoyed.